In my presentation, there will be some slides in German, but I will explain them. Please feel free to drop your questions in the questions chat. I will answer them afterwards because my presentation is in full screen mode and I can't see the chat. So let's start with a short agenda, what you can expect from this presentation. First of all, I will start with the purpose of an active power filter as we see it, and then with what's the actual issue with power fluctuations from wind power, and afterwards some part of the designing process of the hybrid energy system and how to operate the system, or what's crucial about the operation of this system. Afterwards, then I will show the setup in our laboratory and some testing results. Last but not least, conclusion and further research. So the main problem of renewable energy sources like wind and solar are the power fluctuations due to their intermittent nature. So the main purpose of our active power filter is to reduce the fluctuations and therefore make wind power more predictable and easier to handle by providing an almost constant output to the power grid. So why are fluctuations a problem at all, you might ask? Good question. In order to provide a stable power grid, it is necessary to maintain a constant frequency in the grid. In the case of Europe, it's exactly 50 Hertz, and the allowed deviation is about 0.2 plus minus 0.2 Hertz stationary and up to plus minus 0.8 Hertz for short-term fluctuations, but that's extreme values. So to provide a constant frequency, you have to make sure that the energy production equals consumption at all times. So this is represented by the scale shown below. So basically more production than consumption means the frequency will rise and vice versa. With conventional power plants like coal or gas or nuclear, it's easy. If there's more consumption, you simply burn more coal. It's not that simple, but you get the point. But you can't say, give me more wind or more sun. So that's a huge problem in the future with 100% renewables. And if we take a look at power flow from wind plants, we can see the problem. So this is an example of the power output from our 100 kilowatt wind turbine from our campus. This is a 30-minute window. And you can see the extreme fluctuation. They are up to 100% in a matter of minutes. I have to mention that this is an extreme example because it's an old technology. It's a small wind turbine, a so-called Danish concept. So modern big wind turbines don't have such a volatile power output, but you always have fluctuations in the wind, and therefore you will always have fluctuations in your power output. And if you think about the future with 100% renewables, you could imagine that we will need storage capacities in order to match energy production with the demand. At least we need some kind of power filtering to make wind power more predictable for the grid operators. So in order to filter the power flow, we need some kind of storage technology. In our case, we combine our wind turbine with an hybrid energy storage system, which I will explain later on, to provide an almost constant power flow shown by the blue curve. So without the storage, we have this volatile flow to the power grid. And with our storage, we could provide something like this steady power output. So we don't want to store energy for days or weeks. Therefore, we don't need huge storage capacities. Our goal is to compensate power fluctuations in the time range of about seconds to hours. So why do we go with the hybrid energy storage approach? Because we want to make use of the advantage properties from different storage technologies. So in our case, we want to compensate highly dynamic peak loads in seconds to minute time range and longer term fluctuations from minutes to hours. Therefore, we need high power density and high energy density. For example, this graph shows the energy density and the power density on a logarithmic scale for different technologies. So the optimal storage technology in terms of energy and power density would be in this area, at least for our use case. So far, there's no technology settled in this area. And so the nearest technologies to this area are double layer capacitors, or so-called supercapacitors, and lithium-ion batteries. In addition to high power density, the supercapacitors have an extremely high cycle life, and which makes them very well suited to often compensating for highly dynamic load peaks caused by gust of winds, for example. But they have poor energy density, and so the batteries will compensate for longer but less dynamic fluctuations. Of course, you could try to compensate everything with the batteries, but this would affect the service life of the batteries, in a big matter. So another important factor is the high efficiency and fast reaction time of the two storage technologies. We don't want to lose much of the stored energy in the storing process. For example, with hydrogen, it's you have high losses due to the heat. And of course, there are more properties to consider, like cycle life, lifespan, self-discharge, cost per kilowatt hour, and so on. But this is just a quick overview to get an understanding from our hybrid topology. So a big question is how large the capacity of the hybrid storage system needs to be for our use case. So because too big means it's too costly, and too small means it can't do what's designed for. The answer depends highly on how steady the power output to the grid should be. Here's an example on how to design a capacity based on a typical power output from our wind turbines. So I measured our wind turbine for a few days. This is a 55-hour window with slow winds and high winds. And so it's a good representation of what we can expect from the wind power. We have here the power in kilowatts. And yeah, this is basically the original power from our wind turbine. So the basic idea is very simple. You just need to determine the power output that is to be allowed into the grid, and the difference is the power you need to compensate with the energy storage system. So in this case, we use a numerical simulation with a first order low pass filter to determine the power into the grid, which is represented by the blue curve. this is way more steady than the original power. And now in the next step, you just need easy saying, you just need to integrate the difference between the blue and the yellow curve, and then you get the capacity you would need to provide this power flow. So this is not power, so it's energy in kilowatt hours. So if we want to provide this blue curve, we need about, and we always have to look at the maximum to the minimum, that's about 20 kilowatt hours. And to consider the fact that batteries should not discharge to 0 nor charge to 100%, in order to provide a high lifespan or cycle life, you should add a safety margin by applying a minimum and a maximum state of charge. So the total storage or energy storage has the net capacity of about 20 kilowatt hours. So this is our net capacity, and a gross capacity of around 26 kilowatt hours. This is for the whole storage. And now in the next step, we want to determine the split between the two storage technologies. So it's actually the same process as when laying out the total storage capacity seen before. You basically split up the total power flow from the hybrid energy system, which was calculated the slide before, by another low-pass filter to determine the power flow for the capacitor and for the battery. So the goal we set ourselves was to reduce the maximum load of the battery to below 50% by compensating the peak loads with the supercapacitor. So this diagram shows the maximum load of the lithium-ion batteries over the needed capacity for exactly this low power, maximum power for the lithium-ion battery. So less load for the battery means more capacity for the supercapacitor is required. But you always have to consider the cost per kilowatt hour is 50 times higher for the supercapacitors than for the lithium-ion battery. You want to find a sweet spot. So with a filter time constant of 2 minutes, you can bring down the maximum load of the batteries from almost 100 kilowatts to around 40 kilowatt. And you only need around 0.6 kilowatt hours in capacity for the supercapacitors. So, and then if you have determined the power, you just need to integrate it. It's like the slide before, and get an idea from the needed capacities. So if we take this 2 minute time constant for our low pass filter for dividing the power between the batteries and the supercapacitors, we actually see that in yellow is the power to the supercapacitors, and in blue the power to the battery. Without the supercapacitors, the battery have to take all this power. So now we could bring it down by over 50%, if you see here. So the peaks are compensating by the supercapacitors, and we just need as low as 0.6 kilowatt hours from the whole 26 kilowatt hour that we have calculated before. So another part of designing the hybrid system is to choose the right topology for our application. So there are different topologies for the same use case. Here are the three of them compared to each other. This is a bit more technical, but stay with me. I will try to break it down. So first of all, we start at the front end, and here we are connected to the power grid via a converter, which converts the three-phase voltage from the grid to DC voltage and vice versa. We need DC voltage to store energy in our supercapacitors or in our batteries. So this basically connects our whole system to the grid, and so-called the grid converter. Then we have the DC link, and we already have DC voltage in here. So after the DC link, we have a DC-DC converter, which can convert from one DC voltage level to another level. For example, if your batteries operate at 48 volts and your DC link is about 700 volts, you need this DC-DC converter to convert this levels. So in example A, we have the supercapacitor in the DC link, and the battery is connected via the DC-DC converter. In this case, the possible utilization of the supercapacitor is very small, because the energy in the supercapacitor is defined by the square of the possible voltage difference, as you can see in this equation. And the possible voltage difference in the DC link is very small, because the lower boundary is determined through the grid voltage, and the upper boundary through the dielectric strength of the semiconductors. So it's about, for our use case, it's about 570 volt to 800 volt. So it's not the best choice, because we can't use the whole energy in the supercapacitors. We're wasting the most of the energy, and since energy cost per kilowatt hour for double layer capacitors or supercapacitors are very high, it's not the best you could do. So in case B, we can use the supercapacitor energy, the total energy of the supercapacitor, because it's separated via another DC-DC converter. And in this case, we also have the most degrees of freedom, because every single converter can be operate at its own. So it's obviously the most expensive topology, because we have more parts, and we are expecting higher losses due to the additional DC-DC converter, because every time you convert something, you have losses. So there are example C, and here we have switched the positions compared to topology A. Now we have the battery in the DC link, and the capacitor is separated by this DC-DC converter. So we can use the whole energy of the capacitor. And we have fewer conversion parts as compared to B, and therefore it's not as costly at version B, and we are expecting higher efficiency due to less path. So we are going with this example for our prototype, and Yeah, in this case, the battery must be designed for very high voltage, so you can't use 48 volt technology, because we are on the 400 volt grid, and that means we have at minimum 570 volts in the DC link. But there are a few things to consider with this topology. The individual converter have different reaction times in terms of how fast they can reach the maximum power. So basically the power gradient. This is represented by this graph. You can see here the maximum power gradient varies between 10 kilowatt per milliseconds up to 95 kilowatt per milliseconds for the DC converter, depending on the voltage level on the supercapacitor or in the DC link, as you can see here. And we have the grid converter, which could have power gradients from around 160 kilowatt per milliseconds to 250 kilowatts per millisecond. This is just one direction. Of course, we have the negative direction flow, and then it looks a little bit different. But yeah, you get the point. They are different in reaction times. So, and in order to protect the battery from highly dynamic load peaks, which should be compensated by the supercapacitor, both converters must be synchronized. Otherwise, the battery will get all the power in the first moments of a load change. So that's exactly what we don't want to have. So how we synchronize the two converters. This is done through an online calculation that determines the maximum value of the slower converter and sets this value as the limit for the power gradient of both converters. So this ensures the maximum system dynamics compared to a fixed value, because the fixed value has to be the lowest of all values in any case. So that would be around 10 kilowatts per milliseconds all the time. And we would waste a lot of potential, because this is a state we don't have very often. Yeah, so in order to research problems in real operation and to prove the practical application for the energy transition, or as we call it in Germany, Energiewende, a prototype of the proposed hybrid energy storage system was built in the laboratory of Stralsund University. To get a sense of what we have built here, this is an overview from the test stand. And on the left-hand side, you can see the block diagram of the test stand. And on the right hand, the corresponding real construction in the laboratory, which is basically divided into 3 parts. So we have this 20 kilowatt engine test bench. We use this to simulate the fluctuations of wind turbines or any other variable source. And on the left side of this big switching cabinet, we have the energy rack, where we have the batteries and the double layer capacitors. So the right side of this is basically full of control and measure elements. The converter cabinet is shown in figure C. This is where the grid converter, as well as the DC-DC converter and the associated filter elements, are housed. In addition, an interference-free current measurement using fiber optic cables are attached on the back of this cabinet. And there's also a rapid prototyping platform called MicroLabbox from DSpace, in which you can implement the control algorithms we are Simulink. This is basically the brain of the whole system. So with the help of the software from the MicroLabbox, so-called control desk, every parameter can be measured and changed at any time online. So it's very good for rapid prototyping. And if we now take a look at the big cabinet and open the left door, in the upper three racks, we have our supercapacitors that are basically 12 modules. Here you can see one module, and we have 12 modules in series, which each of them has 48 volt, 165 farad, and in total it's a capacity of around 0.64 kilowatt hours. And down below in the four racks below, we have our lithium-ion battery. It's actually 3.5 racks because in this rack we have also a battery management system. And yeah, basically this is one rack, and we have in total 200 cells in series. Each of one cell, you can see here, is 3.2 volts and 40 amp hours, which make in total 25 kilowatt hours. So here you can see the difference in energy density, because this is almost the same space, but the difference in energy density is around of a factor of around 40. So this is a huge difference. Yeah, here are some testing results from the laboratory. This is a 10-minute window of a test with the active power filter. Here you can see the power, and this is the time in seconds. In the upper graph, you can see the power distribution between the generator and the grid connection. And down below, you can see the power distribution inside the hybrid energy storage system. So basically, the yellow curve is the active power of the generator. And this is basically the original power flow I measured from our wind power plant, just scaled down by a factor of 6. And the purple curve is the reactive power, which is needed to magnetize the generator. And the blue curve is the active power we are providing to the grid here. And the red curve is the reactive power from the grid. So you can see that we are also providing the reactive power for magnetizing the generator. So if we take a look at the graph down below, we can see the power distribution inside the hybrid storage system. In red, we have the total power, which is compensated by the total energy storage. And in green, we have the less fluctuating power to the battery. And in purple, it's the highly volatile peak loads. They are compensating by the supercapacitor. And yeah, you can clearly see that the highly dynamic peak loads are absorbed by the supercapacitor, and the longer term fluctuations with more energy but less power are absorbed by the battery. So the dynamic calculation of the maximum power gradient works as we expected. And okay, I have to say here we have a time constant of about 4 minutes, so we can see fluctuations in this short time window of 10 minutes. Yeah, last but not least, conclusion and further research. So combining wind power with storage technology is a good way to make wind power more predictable and therefore more sustainable. Especially important for grid operators because they have to manage demand and supply in the whole grid. The use of double-layer capacitors can significantly reduce the stress on the battery in an active power filter application like this. So further research are to what extent can the service life of the battery actually be increased by using double-layer capacitor? And this is not easy to answer because it's highly dependent on the individual power output of a given grid connection point. So maybe in other applications, it's not needed to use a hybrid system like this. Maybe it's just a battery. And we want to research what kind of ancillary services are additionally possible with this storage system. And if we consider 100% renewables in the future, we might expand the hybrid energy storage by further technologies like power to gas or redox flow batteries in order to store energy in a bigger scale, because you can't store every amount of energy just with batteries. That would economically make no sense. Yeah, thank you for your attention. I'm now open to questions. So the question is, batteries are potential in the future, but do you have a problem, for example, recycling of used batteries? Yeah, recycling is, of course, a big question, and I think you have to recycle it in the future, and there will be some techniques to make it economically possible, and this must be the future. So we can't dig up the whole world just to get our lithium and the other parts for our batteries. We need to recycle it, and I know a few companies that are making huge progress in this area. There's another question. Apart from application of the hybrid energy system in wind turbine, could you please tell us any application in any other renewable energy technology? Yeah, you can basically combine this system with every variable energy source, for example, like photovoltaic. So with PV, you have this also some fluctuations caused by cloudy days, and there you have some extreme power gradients that you can compensate for with, for example, the fast-acting supercapacitors, or if you want to save energy later for the day when the sun is going down, you could use batteries basically. What is the lifespan of batteries used in this technology? By how much? So the first question, what is the lifespan? That's not easy to answer. There's always a two lifespans, the calendar lifespan, which is about 10 to 20, sometimes 30 years. And then you have the degradation through repeating cycles. So, and that all depends on how often do you charge and recharge the battery, and to what extent, and with what power gradients. So it's not easy to answer in how much you can extend the lifespan, because it's always highly dependent on the power flow at a given point. So that is a multi-dimensional question or problem, not easy to answer. In general, which renewable energy is the most suitable to save energy? To save energy with a storage system, it should be very efficient. Otherwise, you will lose a lot of energy in the converting process. So batteries are very efficient, but they are not. You can't use them for storing terawatt hours of energy, because that would be too expensive. So it always depends on the application. By how much would its lifespan increase if it was meant to be used as a standalone energy storage? I assume this technology would increase the lifespan of batteries even. Yeah, it's, as I said, it's highly dependent on the load curve you will use it, because if you have just one load cycle per day and not a high power gradient, you just don't need a supercapacitor, because that's not very volatile, and there are no highly or high peak loads that you can compensate for. So it would not make any sense to combine, in this case, a battery with a supercapacitor. That's just for specific, very fluctuating power curves. So I guess there are no more questions. And as I said before, feel free to write me an email if there are any questions. And yeah, thank you.
Thank you very much for the presentation. And hopefully we see each other next year.
Yeah, I hope so too.